Hello students, welcome back to the classroom point. In our today's class, we are going to discuss the vaporization, vapor pressure and boiling point. In our previous class, we have already finished the solubility and how the solubility of the solids in liquids and gases in liquids affects. After that, the continuation video is about the vaporization, vapor pressure and boiling point. So let's begin the class now with the concept of vaporization. The spontaneous escaping of liquid molecules into gaseous state is called vaporization. So let us see how the vaporization is a spontaneous phenomenon and why the liquid molecules are vaporizing or going into the gaseous state from liquid state on their own. So if we take a liquid, imagine this is a liquid or water in a beaker. So this is a completely enclosure in which the liquid is placed. When we observe this liquid, the liquid is having the mainly two type of the molecules based on the intermolecular attractions. The molecules which are present on the surface of the liquid and the molecules that are present on the bulk of the liquid. So these two molecules, the molecules which are present on the surface, so we can say that surface molecules, and the molecule present in the deep of the liquid, we can say that it is the bulk of the liquid molecule. Now these two molecules face different type of intermolecular attractions. Those are, if you see the surface molecules are attracted only this side, half side, remaining half is completely free. So these molecules are attracted to the other molecules like this, only in the halfway. But if we take the molecule that is present in the bulk of the liquid, it is surrounded by all the other liquid molecules from all the directions. So that the molecule present in the bulk of the liquid experiences more number of intermolecular attractions compared to the molecule present in the surface of the liquid. Since intermolecular attractions are less for the molecules present in the surface of the liquid, they have the higher kinetic energy compared to the molecules in the bulk of the liquid. So whenever kinetic energy is more, so that they need very less energy or negligible amount of energy to go into the vapor state or gaseous state, so that the molecules in the surface only will start going into the gaseous state in the form of the vapor. So that during this process, they occupy all the available space above the surface of the liquid. And these molecules do not go into the vaporization process because they have the higher attractive forces and less kinetic energy. So here the molecules are spontaneously escaping into the gaseous state without providing any amount of energy. That's why we can say that the spontaneous escaping of the liquid molecules into the gaseous state is called the vaporization. So this process we can call it as a vaporization. And once the liquid enter into the vapor state or gaseous state, now all these molecules in the form of the gas, they have the all gas properties. So that according to the kinetic molecular theory of the gases, these molecules can move randomly in all the directions with high velocities, so that these molecules may collide with each other and also with the surface of the liquid molecules. Whenever these molecules collide with the surface of the liquid, again they get attracted towards the liquid by applying some attractive forces. So again this gas start converting back into the liquid state. That process is known as the condensation. So here both vaporization and condensation takes place in the opposite directions. And one more thing is, once these surface molecules are leaving to the vapor state, a new surface will be created that start entering into the gaseous state. So that every time surface molecules are entering into the gaseous state but not the bulk of the molecules, so we can say that the vaporization is a surface phenomenon. Now let us see what factors shall influence this vaporization process. There are some factors that influence the vaporization. First one is surface area of the liquid. Just imagine when the surface area of the liquid increases, more molecules in the bulk of the liquid also come to the surface area. Whenever they come to the surface area, attraction forces decrease so that their kinetic energy increases. So evaporation becomes very easy. That's why when surface area increases, vaporization also increases. And next one is temperature. What happens if temperature is raised? When temperature is raised, that helps in breaking off these attraction forces very easily, so that molecules conversion into the vapor state also becomes very easy. That's why increase of the temperature also increase the vaporization process. And next one is nature of the liquid. Liquids are of two types here: volatile liquids and non-volatile liquids. The liquids in which the intermolecular attraction forces are too strong, they cannot go into the vapor state easily. If the intermolecular attraction forces are very weak, they can easily go into the vapor state. That means in the case of the volatile liquids, the intermolecular attraction forces are very weak, so that these molecules can easily escape into the gaseous state. So the liquids which can easily form the vapor are known as the volatile liquids. So volatile liquids are due to the weak intermolecular attractions. These weak intermolecular attractions make these molecules to go escape easily into the vapor state. So that vaporization again increases in the case of the volatile liquids. Example, you can see that petrol or alcohol molecules which can easily enter into the gaseous state even at the room temperature. Now, non-volatile liquids. In the case of non-volatile liquids, they cannot form the vapor easily. That means they are having the strong intermolecular attraction forces. So, non-volatile liquids are having strong intermolecular attractions. Since strong intermolecular attractions are there, they cannot escape into the vapor state, so that vaporization also shall be very less. Example, cooking oils are there. Those cooking oils cannot vaporize at the normal room temperature. They need the higher temperature. That is the reason why we are using the oils for the cooking purposes. And fourth one is flow of air current. We need to see how the flow of air current is affecting the vaporization process. See, here we have taken the closed container. Instead of the closed container, if you remove this cap and allow the molecules to go into the atmosphere, whatever the air is passing over the surface of the liquid will take over these molecules easily, so that the liquid finds the again empty space above of it, so that its evaporation also gradually increase. That is the reason why if you see that tea, whenever we take the tea, we keep the tea into the saucepan, so that whenever you blow the air, automatically the vaporization process increase and exchange of the heat energy also shall be very easy. So here the molecules, whenever flow of air current increases, that air molecules can take these vapor molecules along with that, so that they are washing away these molecules and creating the new empty space for the vaporization, so that evaporation process also increase. So we can say that when flow of air current over the surface of the liquid increase, vaporization also increases. Now let's come back to the again same diagram with the closed container, and here we shall discuss what is vapor pressure. Let us continue the same vapor pressure concept with the same diagram. Vapor pressure is nothing but the pressure exerted by the vapor on its own liquid surface. So after vaporization is done, gas, all the liquid molecules are present in the form of the gas, so that they can exert the pressure on its own liquid surface. That pressure is known as the vapor pressure. But where we can call the actual pressure of the vapor as a vapor pressure? Let us see here, we discussed the two things here. That is both vaporization and condensation process. Vaporization, condensation process both are opposite in nature. And if you leave this system for a long time, the vaporization and condensation continuously to takes place. Afterwards, they reach a stage where the rate of vaporization is equals to rate of condensation. This state is called as the equilibrium. At equilibrium, whatever the number of molecules entering into the vapor state shall equals to the number of molecules leaving the vapor and coming back to the liquid state. That means the total amount of the vapor above the surface of the liquid remains constant. So vapor remains constant. Since vapor remains constant, there is no change in the number of vapor molecules. That time whatever the pressure is exerted by the vapor on its own liquid surface is called as the vapor pressure. And this vapor pressure is also known as the saturated vapor pressure, because the system already occupied the entire space available for it and reached this stage of saturation. That is the reason why equilibrium is established. Equilibrium is established only in the closed containers, not in the open containers. Why? Because in the case of the open containers, as we discussed earlier, flow of air current will take the molecules away from the surface of the liquid, so that the vapor molecules will not get the chance to come back into the liquid state, so that equilibrium cannot be established. Now, let us see which factors influences this vapor pressure. The vapor pressure is influenced by two factors. They are temperature. Second one is nature of liquid. So how temperature is influencing the vapor pressure? As we discussed, now when temperature increases, when you heat it, then the temperature helps in the breaking of these intermolecular attraction forces. Molecules becomes free. Evaporation also becomes very easy. More vapor will be formed so that can exert the more pressure on its own liquid surface. So by increasing the temperature, vaporization increases and vapor pressure also increases. Now, there is a relation between the temperature and the vapor pressure that was given by the Clausius and Clapeyron. So this equation is popularly known as based on their name only, that is Clausius and Clapeyron equation, according to which the vapor pressure is equals to A into e power minus delta H enthalpy of evaporation by R into T, where P stands for the vapor pressure and here delta H is nothing but the enthalpy required for the evaporation process. R is universal gas constant, T is the temperature, A is the Arrhenius constant. Now apply the logarithm on both sides so that we can get the ln P is equals to log A minus delta H evaporation by R into T. Then convert this one into the base 10 logarithm. So we get log P is equals to log A minus delta H evaporation by 2.303 R into T. So this we can write down as log P equals to log A minus delta H evaporation by R into 1 upon T. So that if you write down if you get a graph between the log P versus the 1 by T, so here we get the Y equals to mx plus C. So here minus mx plus C. Slope is minus, so that we get the graph in this manner. Log P versus 1 by T. So that negative slope, here intercept value is equals to log A and this is equals to slope. Slope equals to minus delta H evaporation divided by R. So if you want to get the delta H, amount of enthalpy of evaporation also can be calculated from this slope. Delta H evaporation is equals to minus slope into universal gas constant. So enthalpy of evaporation means energy required for the evaporation also can be calculated using this particular formula. Now let us discuss how the nature of liquid is influencing the vapor pressure. As earlier discussed, liquids again of two categories, volatile liquids as well as non-volatile liquids. Volatile liquids have the weak intermolecular attractions so that their evaporation shall be very high, so that they can form the more vapor and also vapor pressure. That means volatile liquids vapor pressure is more. And non-volatile liquids, if you take, they cannot evaporize very easily. They need some more amount of the temperature, so that the vapor is also less and the pressure exerted by that less amount of the vapor also shall be very less. That's the reason why vapor pressure is less. So here nature of liquids means volatile liquids have high vapor pressure, whereas non-volatile liquids have low vapor pressure. Now let us discuss how boiling point is related to the vapor pressure. So now let us discuss the boiling point. I shall write down the definition of the boiling point first here. The temperature at which the vapor pressure of a liquid is equal to atmospheric pressure. is called its boiling point. So here, that means whenever the vapor, whatever is created, that must be equals to the atmospheric pressure. So I will take the open container now. Liquid in the open container, and the molecules normally vaporize at normal temperatures also, that we are calling them as a vaporization process. And this vaporization process usually not equal, cannot create the pressure required to oppose the atmospheric pressure, because the entire surface of the liquid is covered by the atmosphere whose pressure is equals to 1 atmosphere. Usually that is equal to 0.987 bar. So usually liquids cannot create the more vapor whose pressure is equals to atmospheric pressure, except some very highly volatile liquids can easily escape into the vapor state, so that they can form the higher vapor and their vapor pressure is also equal to atmospheric pressure. That we shall discuss in the coming points. Now, initially the vapor pressure of the most of the liquids is not equal to atmospheric pressure, so that it cannot boil. But now whenever you are heating, whenever temperature is raised, this temperature helps in increasing of the kinetic energy of the molecules and breaks the attraction forces, so that more molecules enter into the vapor state, so that pressure gradually increases. Whenever the pressure generated by the vapor is equal to atmospheric pressure, then we say that the liquid starts boiling. For example, let us take the water in this container. This water boils only at the 100 degrees centigrade, because at 100 degrees centigrade its vapor pressure is equals to 1 atmosphere. That is the reason why this 100 degrees centigrade is also known as the normal boiling point of the water. Standard boiling point is measured at the bars. That's why here 99.6 degrees centigrade is known as the standard boiling point of the water. Now, which factors influence the boiling point? Opposing pressure. Here opposing pressure is there, no? This opposing pressure influences the boiling point. If you increase the more pressure, then you need to create more vapor so that its pressure is equal to atmospheric pressure. To create the more vapor, you need to increase the more temperature. So when temperature increases, we can say that boiling point value also increase. Imagine now water vapor pressure is equal to 1 atmosphere at 100 degrees centigrade. What happens if 2 atmospheric pressure is taken? If 2 atmospheric pressure is taken, water do not boil at 100 degrees centigrade but boils more than 100 degrees centigrade. If atmospheric pressure is less, then water not necessary to boil to go temperature up to the 100 degrees centigrade, but even boil at the lower temperatures. Let us take an example. Now you take this water to the higher altitudes. Imagine this is the peak of the mountain. At Himalayan mountain, the atmospheric pressure is 0.5 atmosphere only. So when you go from the sea level to the peak of the mountain, the pressure, atmospheric pressure decreases. So when the atmospheric pressure decreases, liquid not necessary to create that much pressure to oppose this pressure. It can easily make its vapor pressure is equals to the opposing pressure even at the lower temperatures. That is the reason why liquids boils at the lower temperature, so that water boils even less than the 100 degrees centigrade at the peak of the mountains like Himalayan range. Now the question is, what happens if the liquid is closed? Imagine pressure cooker. So in the case of the pressure cooker, whenever you heat, initially evaporation gradually takes place. The entire space is occupied by the liquid molecules in the form of the vapor. Since that vapor pressure can never be equals to the pressure of the lid, that is the reason why the liquid in the pressure cooker or closed containers never boils. Then what happens? Simply, it reaches a stage where evaporation is not possible, then suddenly liquid expands. So expansion of the liquid takes place and entire liquid exists in the form of the vapor. But liquid do not boil in the pressure cooker. Then whenever you observe, when you open the pressure cooker, you can observe that the liquid is boiling. How could this happen? That means before opening the lid of the pressure cooker, we release the pressure using the nozzle, so that some amount of the temperature and pressure both leaves. Afterwards, when you open the lid, by then the vapor whatever present inside of the liquid gets condensed, because we already released some amount of the pressure and temperature also. Condensation took place. The moment when you open it, since the entire temperature do not come to the room temperature, the liquid looks like it is boiling. But actually in the closed container like pressure cookers, liquid do not boil. That is the reason why whatever the materials, cooking materials or the food materials we are taking in the pressure cooker, they boil they boil very easily and very speed. The reason is the water can take the temperature up to the 800 degrees centigrade. Normally up to 100 degrees centigrade the water evaporates. So that water in the open containers can allow the temperature to go to the cooking material up to 100 degrees centigrade. Once 100 degrees centigrade temperature is reached, since water is leaving the container, so it cannot transfer the heat energy from the heating area to the cooking material. But in the closed containers, since no boiling occurs, water can go to the temperature up to 800 degrees centigrade, so that the entire energy whatever it is taking, it transfers to the cooking material and cooking process becomes very easy. It is not by increasing the boiling point, because there is no boiling process for this. By closing, only transfer heat takes place very fast and more amount of the heat takes place in the less amount of the time, so that the cooking process becomes very easy. So here, when pressure increase opposing pressure, then automatically water, whatever the liquids, boils at the lower temperature. Now, higher temperature, because of pressure increase means temperature also increase. Now we can take that what type of liquids having the different boiling points. The boiling point depend upon the nature of the liquid here also. Nature of liquid. Volatile liquids can form vapor very easily, and their vapor pressure can easily become equals to the atmospheric pressure. For example, if you take the volatile liquid, even at 25 degrees centigrade, it can form the more amount of the vapor, so that its pressure is equals to atmospheric pressure very easily, and it boils. That's why volatile liquids boils at the lower temperature. So volatile liquids have low boiling point because they have the higher vapor pressure. What about the non-volatile liquids? Non-volatile liquids do not form the more vapor easily, so that they need more temperature to create the more amount of the vapor, and that vapor is creating the pressure equals to atmospheric pressure, which needs the higher temperatures. So that non-volatile liquids have the high boiling point because of the less vapor pressure. Now coming to the vapor pressure and vaporization, we need to discuss one important point here. Vaporization is a surface phenomenon which depends on the surface. When surface increases, vaporization also increases. Vapor pressure is not the surface phenomenon. How this is not the surface phenomenon? Vapor pressure is nothing but the pressure exerted by the vapor on the unit area of the surface of the liquid. Imagine the vapor molecules are exerting the pressure at this unit area is equals to 1 atmosphere. And in this unit square area is also equals to 1 atmosphere. Here also is equals to 1 atmosphere, and here also equals to 1 atmosphere. That means if you add all this, can we say that it is equals to 4 atmospheres? We cannot say that. So that vapor pressure is calculated only for the unit area, whatever the length of the surface it may be. Only vaporization increase, vapor pressure remains same at the given conditions of temperature. So dear students, I hope you understand today's class. So we shall meet in the next class. Thank you one and all.